Welcome to your science lecture. This is Professor Diane L. Pomeroy. This week we're going to begin an overview of oceanography. Oceanography is a survey of the properties of the world's oceans. In this part, the second part of the overview, we're going to learn about oceanic circulation, ocean pollution, and oceanic ecosystems, in particular focusing on wetlands of Southern California. Ocean currents are masses of seawater that flow from one place to another. Think of them as rivers of the ocean, both at the surface and beneath it. Surface currents are wind-driven masses of water. Deep currents are density-driven masses of water. The surface currents of the world's oceans are not only influenced by the wind, but also the distribution of Earth's continents, gravity, friction, and the Coriolis effect. The last three generate a phenomenon that's known as the Ekman spiral. Ekman transport and the Ekman spiral are surface currents that are generated due to the Coriolis effect. As the wind blows across the surface of the ocean, the friction of the water due to its high surface tension will increase, and displacement of the surface water will begin. As water layers are continuously replaced at depth, they move in a spiral that eventually deflects the water 90 degrees to the direction of the oncoming wind. The deflection of wind and water in a given direction, and at different speeds on the ocean's surface, also generates what are known as geostrophic currents, or gyre systems. This image illustrates what's happening in a gyre. So the deflection of wind and water in a given direction is what's causing this difference, this hill of water to form. So we've got the Coriolis of force operating in the opposite direction as gravity, and it's going to create this central hill of water that we observe, which from an aerial view generates this circular form known as a gyre. Eastern boundary currents in a gyre move slowly, and western boundary currents move quickly. These differences in motion and gravity again are what generate that center, the central hill at the center of that gyre. Gyre systems are patterns of surface circulation where multiple currents of seawater converge. These currents have distinct temperatures and densities, as shown on this map of the world. The movement of gyres is dependent upon the Coriolis effect. So in the northern hemisphere, winds and waters are deflected to the right, and in the southern hemisphere, winds and waters are deflected to the left. There are 5 gyre systems around the world, and they're divided according to the hemispheres for the Pacific and Atlantic. So we have the North Pacific, the South Pacific gyre, the North Atlantic, South Atlantic gyre. We also have the Indian Ocean gyre. The North Pacific gyre system consists of 4 main currents. The North Pacific current, which flows in the northernmost latitude around 60 degrees or so, the boundary point between 30 and 60 degrees. We've got the California current, which flows southward from the North Pacific along our coast. The North Equatorial current, which flows westward, and the Kuroshio current, which flows northward along the Japan coast. North Pacific current is a cold water current. So is the California current. North Equatorial current, because it's flowing along the equator, generally has warmer water. And that warm water, as it flows northward, actually moves very quickly, because remember again, the eastern boundary current here is the California current, flowing much slower than what we have in the west with the Kuroshio current. So these differences in speed have an effect on the temperature variability of each of those oceans along each of those sections of the Pacific Ocean along those coasts. Gyre system strength is dependent on the winds of the Earth. Changes to atmospheric temperature, along with wind speed, result in changes to Earth's climate over time. The exchange of surface and deep currents is also critical to climate change. So on this diagram, we have different climatic regions of the world's oceans. We've got equatorial, tropical, subtropical, temperate, subpolar, and polar. You'll note that along the equator, we have equatorial and tropical climates. So those are generally humid and hot. As we move into the greater latitudes, that temperature will begin to cool off, and the air mass will also begin to lose its water. It'll become more dry over time until we approach the poles, where again there's excess moisture that is absorbed, and those air masses are cold and moist, and so there's a lot of excess snowfall at the greater latitudes of Earth's surface. So changes to these climate latitudes are going to happen as the sea surface temperature increases. That means those bands of, let's say, equatorial tropical climactic regions are going to increase. Thus, at higher latitudes like 20 and 30 degrees, we're actually going to get more humid climate over time than is expected or is normal for where we are in the subtropical desert belt of the world. Now that's all surface circulation. So gyre systems, what I've been describing to you so far, are part of surface circulation of the world's oceans. Recall what I brought up at the beginning, which is that there's not only surface currents, but there's also deep water currents. Deep currents develop due to differences in salinity and temperature of the water. This generates a phenomenon known as thermohaline circulation. Thermo, meaning temperature, haline referencing salt. So deep water currents, they contain excess amounts of salt in their flow, and this is because deep water currents originate at the poles. So at the poles, what's happening is that surface ocean water is freezing. As it freezes into sea ice, excess salt, okay, and the ocean surface begins to sink to the depths. And so deep water currents carry those incredibly cold, deep saline waters from the poles all the way down towards the equator. So at the ocean basins, we have these deep water currents that are flowing, and they carry different amounts of salt, different amounts of other particles, things like dead phytoplankton and dead zooplankton, and various other bits and pieces of sediments and other organisms. Those currents get carried in incredible depths in the ocean, and again, they meet at the equator where they're exchanged with surface waters, and that's what generates this circulation pattern. So this circulation pattern originated around 2 million years ago when the Atlantic and Pacific Ocean current flow was cut off from each other. Prior to that point, there was an exchange between Atlantic and Pacific Ocean flow. That's no longer happening, and so what's happened now is this type of thermohaline circulation we have as shown on this diagram from the UNEP. There's many types of deep currents or bottom waters, intermediate waters, and surface waters in the ocean. This diagram shows the interaction between three types of deep water currents in the Atlantic. So we've got the Antarctic bottom water current, which again originates from Antarctica from the south, the North Atlantic deep water, which originates from the North Pole, and then we have the Antarctic intermediate water, which originates again from Antarctica, as well as surface waters from the Mediterranean. So all of these waters mix at the equator, and again the deep waters flow from the poles to the middle of the Earth surface, and again this is due to patterns of Earth's rotation and patterns of oceanic and atmospheric circulation. Each water mass is suspended above the other in order of density. The Antarctic bottom water, referenced as AABW, is colder and saltier than the North Atlantic deep water, NADW, which in turn is colder and saltier than the Antarctic intermediate water, AIW. So as these water masses converge with each other, there's distinct differences in their densities. The Mediterranean outflow that's here in warm surface waters, they mix with the deep waters at the equator. And so that shows, again, this thermohaline circulation, how critical it is for the mixing, overturning of these deep waters with the surface water, because this process of overturn allows for these very rich sediments and salts to rise to the surface. It allows for particular phytoplankton and other organisms to thrive in different environments at different times of the year. And so without thermohaline circulation, oceanic ecosystems as we know it would collapse. And in fact, this is what happened during the Permian mass extinction event. It's theorized that this phenomenon, similar phenomenon, had happened where this exchange of deep water and surface water stopped, mixing of the ocean stopped, and so When the ocean does not mix anymore, then again ecosystems slowly begin to collapse from the bottom up in terms of the food chain. So the conveyor belt moves much slower than wind-driven currents, depending on flow, temperature, variability with seasonality, depending on, again, sea surface temperature and mixing. All of these phenomena control this process of thermohaline circulation. What's interesting to note is that when we get into the deeper water of the ocean, 1 cubic meter of water takes about 1,000 years to circulate in the global conveyor belt system. Now, this information is also important in understanding the outflow of oceanic pollution, which I'll mention at the end of the lecture. So this exchange, again, is vital for the growth of the base of the marine food chain. That's phyto and zooplankton. For more information about marine life in the ocean, feel free to go ahead and check out my oceanography lecture series, which is posted on YouTube under the oceanography playlist. So with all of this flow of surface currents, with wind and wave patterns that we've learned about in the previous lecture, and with this understanding of how currents work, water currents are an excellent way for which the coastline to be shaped. So what exactly is a coastline or a shoreline, because those terms are interchangeable? Well, when we talk about coastlines, we're talking about 3 parts to the beach, 3 parts to the essential coastline area. So we have the coast, which is the land surface. We have the shore, which is the sea, the ocean itself, the shallow sea, and we have the coastline or shoreline, which is the boundary between those two. So coasts are shaped by the wind and water primarily, so wave action will sculpt at the coast over time. However, coastal shape is also determined based on the continental shelf shape. So some coastlines have wide continental shelves and some coastlines have narrow continental shelves. And this has an effect on the different features that we can observe on the coast itself. So the coast is the land surface, again, the shore is the water, and the coastline or shoreline is the boundary between the two. Coastlines themselves are areas of deposition in which sediment such as sand becomes deposited in a region that we call a beach. And this sediment is subject to erosion, not only due to wind and water, but also due to wave action on a daily basis. This diagram of a beach shows several key terms. Let's start with the shore, or shallow sea, on the right. There's 4 portions to the shore. Offshore, where the fully developed sea ends. Nearshore, where breakers form. Nearshore is also referred to as the surf zone. Foreshore, where the beach sand begins. Features like berms, think of a berm as almost like a line of sand or sediment, okay? And scarps can form here. And the backshore. This is where the water line will end and sand dunes can begin to accumulate and form in this part of the beach. This diagram also shows the level of high and low tide, as well as longshore bars. Bars are like berms. They're lines of sediment that accumulate, but in this instance, they accumulate due to longshore current. As waves crest and hit shore, they bring sediments, such as shells, sand, and mud, along with them. Movement of sand that's perpendicular to the shoreline is called swash and backwash. This illustration shows the motion of swash, which is away from the breaking waves and onto land, and backwash, which is moving back towards the breaking waves and out to sea. So there's this constant perpendicular flow of sand, again that's referred to as swash and backwash. This slide shows swash and backwash in another illustration, this time along a sloped beach face. The greater the energy of the wave, the more that the beach face will be eroded by a strong backwash flow. This slide has a photograph of swash and backwash on a flat beach. The energy from the waves dissipates totally as it approaches land, creating very little erosion, unlike the previous slide. So recall that waves themselves, whether they're ocean waves or sound waves, that's energy displacement. Okay, so as waves approach land, what's happening is that frictional force is going to cause the wave energy to stop or slow down, and that's what's going to cause the shape of those waveforms to change. And swash and backwash is just one example of that exchange of energy between the land surface and the ocean. This slide shows the other exchange of energy that happens as the waves move inland, and that's known as longshore current. Now, one of the dangers of longshore current is a phenomenon known as rip current. So rip tide or rip current happens as longshore current moves parallel to the beach. Longshore current itself is a flow of water, so it's the flow of seawater that's moving parallel to the beach. Longshore drift is what happens when longshore current, as it moves, deposits sediment along the coastline. So note that longshore current is parallel to the beach face, and as the waves break and as they move towards the land, that swash and backwash pattern that we observed in previous slides, that pattern is perpendicular in the surf zone. This slide has a photo of longshore current that's moving parallel to the beach. So as waves break in the surf zone and as they hit land surface again, and because of the differences in the shape of the continental shelf and slope, you get differences in the type of coastline that we can observe. There's two different categories of shoreline features that exist, and these are classed as either erosional or depositional. Erosional shorelines develop due to high amounts of wave action, while depositional shorelines develop with less wave action. These images depict different features in each type of shoreline. Let's discuss erosional features first. Erosional shorelines tend to have narrow beaches. They have narrow continental shelves that are steeply sloped. Erosional shorelines have large cliffs that are eroded by waves in the surf zone. So we've got large cliff, narrow beach, and then there's the ocean. And that's what most of our coastlines are like in Southern California. Most of the time we have erosional coastlines or shorelines here. So as the wind and water hit the surface of the rocks and the cliffs, a process known as abrasion will occur. Abrasion is when rocks collide with one another and they break down into smaller pieces. So as the waves break and hit the slope of the land surface, sediment carried in those waves will hit the sediment that's already on land, and in this way it'll slowly grind down the land surface. And this will especially affect softer sediments, so things like muds and silts are more readily affected by this process than, say, coarser grained sands or possibly conglomerate type gravels, right? Those types of energy, that type of energy is different there. So the energy from waves in the ocean can also break down rock surfaces itself over time, sometimes through salt as well. The salt that's present in the ocean can also gradually erode rock. And so that process where, waves are just crashing against the side of a cliff, that's known as hydraulic action. So taken together with both abrasion and hydraulic action, what happens is that cracks and crevices in the rocks can begin to form in the cliffs, and those can eventually grow into caves and then arches, and over time with erosion of the topmost portion of that arch, stacks can form. So this illustration shows how that process of repeated breaking of waves on the cliff can develop each of those features that we find in an erosional shoreline. So gravity, wind, and pressure will cause the topmost portion of that arch to kind of break away and develop into a column of rock that we call a stack. This slide shows some of the erosional features I mentioned on the previous slide. In some photos, we've got a beach, we've got Dana Point Harbor from 1920, so from 100 years ago, this is what Dana Point looked like. And we also have a more modern photo of Spain with some sea caves and an arch. So the Dana Point Harbor image shows some cliffs there, very narrow beach. We've got what we call a wave-cut terrace, which is another name for a sea cliff here. And there are some features here like tide pools and things that still exist. But as you'll see in later slides, we have modified our beach so it's more depositional than erosional. Depositional shorelines, they tend to have wider beaches that are more tidally dominated, and this happens because these beaches form on wider continental shelves, and these shelves are more gently sloped. This allows sediments to gradually build the coast over time, especially as rivers empty out into the ocean. Depositional shorelines are defined by these features here. They're shown on this image. We've got some lagoons. embayments and barrier islands on this illustration, along with longshore current. So longshore drift and longshore current are what help to build up these depositional shorelines over time. Now, we don't really have a whole lot of depositional features here. We do have a few that are left over from the 1800s that are remnants of what used to be here. So hundreds of years ago, our coast was a natural depositional coast, but we've since altered it, and I'll talk about that in a little bit. So instead, let's go to the East Coast. So on the East Coast of the United States, there tends to be a lot more depositional features, depositional shorelines. So this slide shows the coastline of the state of New York. Long Island is a barrier island. Barrier islands develop due to excess deposition of sediment, usually by longshore drift. This island cuts off the flow of the Atlantic Ocean, and that's what causes water to kind of refract or bend around the barrier island and lose energy as it crests on shore. This excess water will then collect in a region that's known as a bay. So that bay, that embayment there, is still connected to the Atlantic, but it's again behind that barrier island. And again, because there's less direct contact between the ocean surface and the land surface, it's a little bit more tidally controlled. There's a lot more deposition of sediment in this area. And because of that, wetland ecosystems will form in this way. Spits are also areas of deposition of sediment. They form a hook-like shape, and again, that's due to refraction of wave energy as the waves approach and bend around that land surface. Most shorelines have a combination of depositional and erosional features, and our coastline is no exception. However, one type, whether it's erosional or depositional, tends to be more predominant than the other, based on, again, the shape of the continental shelf, wave energy, and also elevation of the land surface above or below sea level. So whenever sea level rises, this also has an effect on the shape of the coastline. The next few slides show the coastlines of the United States and whether they're primarily erosional or depositional in their coastal features, starting with this one. Pacific coastline, which is our coastline included, it's tectonically active. So what this means is that we're not only situated on this plate boundary here, this transform boundary with the San Andreas Fault, but the shore is constantly going to be exposed to erosion and storm surges. And note how narrow the continental shelf is here. So again, a lot of our beaches and features are erosional features here because of all these processes. The Gulf of Mexico, on the other hand, is a little bit different. Note how much wider the continental shelf is here. In addition, because of the lack of flow from the Atlantic into this region, the Gulf of Mexico is definitely more tidally dominated, so there's a lot more swamps and, in this case, bayous and other coastal features that we find associated with depositional environments here. Now, severe rates of flooding do occur, typically during hurricane season, during severe storms and hurricanes, but again, for the most part, these beaches are depositional in nature. Finally, once more, we have our Atlantic seaboard. So this is the east coast of the U.S. We've got deposition of sediment here. Note again how much wider the continental shelf is here, especially by the Florida panhandle area, parts of the south. You'll note that there's, again, excess deposition of sediment here, excess swamps, and those types of wetland environments can easily form here. So while nature does most of the work in shaping the coast, humans have altered the landscape drastically over the past several hundred years, and this is primarily due to the Industrial Revolution. So starting in the 1800s, when we started to manufacture things more, cities began to develop and take over various natural environments. People began to inhabit coastal regions more as well. And so the reason why we inhabit coastal regions, and people have been doing this, indigenous people have been living along the coast as well for thousands and thousands of years prior to the Industrial Revolution. But people have been inhabiting coastal regions primarily due to the mild climate. And the mild climate is in part due to this process that's shown on this slide, which has to do with temperature regulation. So what's interesting about, what's known about the ocean is that the ocean is a heat sink, right? So the ocean will absorb excess amounts of heat that are accumulated in the atmosphere during the day. And from this process, the air that flows across the surface of the land, if it's closer to the ocean, is much cooler And so because of this cooler air, there's a lot more mild climatic change in temperature here along the coast than what we have further inland. So for people that live further inland, right, weather tends to be a lot more extreme. So during the day, for example, temperature can skyrocket to over 100 degrees in the summertime, and then at night it can go down to maybe like the 40s or 50s. And these extremes in temperature on a daily basis are much more noticeable inland than they are along the coast. And so that's part of the main reason why so many people live along coasts globally, not just here in California, but everywhere. So it's a mild climate. It's also an abundance of food and natural resources like oil and natural gas, which are easily extracted from offshore and onshore coastal environments. So coasts have been modified, again, since the Industrial Revolution primarily, and they've been modified to make way for ports, piers, and this increasingly dense human population along the coast. On this slide is an image of Laguna Beach from 1920. Note the position of sea level, the rugged terrain and cliffs, and this wider swath of beach. So here we've got all of these cars parked on the left, and we've got people on the right that are heading out towards the beach. Notice where the water line is, and notice the housing, the trees, the hills. Keep this image in your mind, because as I move to the next slide, you're going to see just how much change has happened in only 100 years. So this is what the same direction, this is what the Laguna Beach coastline looks like now. Sea level has risen, and it will continue to rise in the next 100 years as well. Note just how many people now are living along the beach in terms of housing. Look how close those houses are to the waterline. Okay, so notice also that the hills have changed in their shape, right? So the entire coastline has been modified by us. We changed coastlines again to make way for harbors and ports like the Port of LA, Port of Long Beach, which are major hubs for economy, but at the same time, we've drastically altered our landscape permanently. This slide is an illustration of Southern California coastline as it was in the 1800s. So the dashed lines here, or dotted lines, represent the placement of the ports of LA and Long Beach. Sections of San Pedro as well are shown here. Notice that at one time, mere 150 years ago, we did have a barrier island here, and we had tidally dominated areas. Over that span of 150 years, those coastal wetlands that we used to have here from the tidal flats, they've been drained and destroyed, and the rivers that naturally emptied in the Pacific have been diverted and essentially funneled into concrete. So the entire coastal shape, we've completely altered and changed it. We destroyed a barrier island here. We took out all the wetlands, and this was all to kind of level out and flatten the area so that ports and harbors could have a sense of, I suppose, like normalcy in terms of water level, so that, you know, as boats can pass through, they're not going to, say, hit like some kind of barrier island or not be able to get in because of excess swampy areas, right? People could easily traverse the landscape, drop off their goods, and go back out to sea once more. And we've been using these ports, again, for hundreds of years, but at what cost? So coastal environments, natural coastal environments, are categorized into three types. These are estuaries, lagoons, and marginal seas, as shown on this slide. So we've got an estuary on the left, we have a lagoon on the right, and we have a marginal sea in the middle. All of these are tidally dominated environments that connect to the open ocean in some way. In Southern California, we have remnants of estuaries that still exist along our coast, and that's where we're going to focus our talk for this week, is on estuaries and wetlands, ecosystems that are derived from them. An estuary is an area of land where a river or body of fresh water meets the ocean. There are four types of estuaries, as illustrated on this slide: coastal plain, fjord, bar-built, and tectonic. Coastal plain estuaries, like Chesapeake Bay in Maryland, form as the river empties out into the ocean. This creates a floodplain environment along the coast, and also wetlands can form in this way. Fjords, like the king of the fjords in Norway, form as a glacier retreats, and that those rivers will then meet the ocean. So for those of you that are fans of the Disney film Frozen 2, you're probably thinking of that line from the film, and that's referencing fjords in that particular region in Norway. Built estuaries, which are shown here with Pamlico Sound off the coast of North Carolina, they form as barrier islands, block flow from the river into the ocean, and that creates this embayment or a lagoon type of environment. So again, that's a bar-built type estuary. So we've got barrier islands or spits that kind of block that ocean flow, and at the same time have enough of a connection to create this lagoon type of environment. Tectonic estuaries, as shown here with San Francisco Bay Area, develop along fault zones or escarpments. Here, the Sacramento River is offset by sections of the San Andreas Fault as it empties into the San Francisco Bay. Most of the remaining estuaries that we have in Southern California are tectonic estuaries. Estuaries can create wetlands. Wetlands, as I mentioned to you before, are ecosystems in which the water table is close to the surface. Most wetlands consist of salt-adapted plants. So in other words, they are adapted to an environment where there's changes in salinity, changes in pH because of changes to tidal level. And they also consist of oxygen-depleted muds and peat deposits. In these oxygen-depleted muds, there are various forms of bacteria that can actually consume and destroy various types of marine pollutants that get into sediments, in addition to enriching and recycling muds and plants that are already present in salt marsh environments. This process is known as eutrophication, and it's critical for maintaining the health of the coastal environment. So there's these two categories of wetlands. We have salt marsh and mangrove swamp. Mangrove swamps are more common in the bayous and parts of the East Coast, and other places around the world as well. We tend to have salt marsh wetlands here in Southern California, which are shown on the left. So as I stated previously, most of our wetlands in Southern California have been dredged and destroyed to create the ports of LA and Long Beach, as well as various harbors for boats, including sections of Newport Beach and other coastal environments here, like Naples and things like that. So these images are before and after Southern California's wetlands, with the top image a representation of our coast around 150 years ago. So in green and yellow, we have all of our estuaries there. In blue are the rivers that emptied out into the ocean. So parts of the Anaheim River are diverted here with Seal Beach. Parts of the LA River are diverted in Long Beach and San Pedro. And so those rivers have now since been kind of dammed up by concrete, and those estuaries, as you can see in the bottom image, are totally drained and destroyed. So here are some images of the Bolsa Chica wetlands in Huntington Beach, California. Its over 100-acre reach has now been reduced to only a few acres at best, with nearby property and roads encroaching on the area. As coastal populations increase, we have more of an impact on the oceans. One of the direct effects of this is marine pollution. There are 6 types of marine pollution I'll discuss: petroleum or oil, sewage, DDT, PCBs, heavy metals such as mercury, and trash. Contamination from all pollutants affects the marine ecosystem through a process known as biomagnification, which is illustrated on this slide. Biomagnification begins when sediments become contaminated and are consumed or absorbed by microscopic organisms, such as plankton, algae, or bacteria in seawater. These organisms are then consumed by several species until the apex consumer, a large species of fish, for example, is reached. At each phase of consumption, the amount of contamination increases exponentially, so that the apex predator in the food chain has the most contaminants in its body. This means that if we consume fish that are living near contaminated sediments, we're very likely to also ingest the contaminants and get sick, or, in rare cases, develop cancer or die. Petroleum, or oil, is a major contaminant in the oceans. Oil spills like the images shown from the BP oil spill in 2010 off the Gulf of Mexico have devastating damage that lasts for centuries. Since oil and water do not mix, again recalling last week's lecture on water polarity, a surfactant is used to clean the spill. So surfactant, think of it as like soap. It's used to pick up and carry the oil molecules away from the water, but the effects of these spills last, again, for a very long time and are circulated in the water for potentially hundreds of years. Sewage is also a major contaminant in the oceans. Between 2017 and 2018, over 2,000 facilities along California's coast reported sewage spills, and over half of those have reached the ocean. Beaches are often shut down for days to weeks due to cleanup of these spills. Sewage facilities are usually processing plants, which recycle or distribute raw sewage that flows in pipes beneath housing, businesses, and factories. This diagram shows the flow path of sewage from your home towards the ocean. While the next two contaminants have been banned from use in the United States, their impact still affects marine life and ecosystems today. DDT is an organochlorine that was used as a pesticide. It was originally made to combat malaria and typhus spreading mosquitoes in the 1940s, but it was discontinued from use in the 1970s due to primarily Rachel Carson's work, Silent Spring. DDT embeds itself in liver and reproductive tissues of birds and other wildlife and wetlands ecosystems. So here's how that process happens with biomagnification. Again, note the parts per million amount in the water. So just a very small amount is all it takes for birds to be affected. So as it embeds itself in the reproductive tissues, what happens is that birds essentially, when they normally lay eggs, birds have hard shells to their eggs. DDT causes those shells to soften. The calcite that's present in the bloodstream of ovulating birds stops being produced. And so the eggs, as they're being laid, are very soft. And so the offspring can't survive the hatching process and they die. Brown pelicans and other predatory birds along our coast, they almost went extinct due to the presence of DDT. PCBs are organochlorines that are used in electronics, such as microchips, carbonless copy paper, and fluorescent tubes. The use of these has been banned since the 70s, but PCBs are still present in sediments from runoff near factories, and have, again through the process of biomagnification, still been found in various species of fish today, especially in parts of the Hudson River. Consumption of PCBs is very toxic to us, including children, and especially children, and can lead to developmental disabilities, cancer, and again, in rare cases, death. This is just some of the impacts of PCBs on our health. And you'll note that about 96% of it comes from our food, again, specifically fish. Next, let's discuss mercury. I don't mean this kind of mercury, unfortunately. I mean this type of mercury. Mercury in fish and crustaceans, like PCBs and DDT, spreads through that process of biomagnification. Now, mercury isn't the only heavy metal that we have to worry about from sea life. There's also arsenic and lead and cadmium, among other metals and other pollutants that exist in the sediment, especially where there was toxic waste that's been dumped. We do have to worry about that as well. So the way that all of those heavier elements are processed is very similar to what happens with DDT and PCBs. Again, it embeds itself in sediment, and various species of plankton and algae consume it or absorb it, and then other organisms eat those in mass, and then over in turn, with the food chain, small fish eaten by larger fish, etc., moving all the way up the food chain until we get to these organisms that are listed here. So this chart shows a list of fish that contain certain amounts of mercury contamination, and it also shows you which fish are safe to eat multiple times a week. So if fish is a main part of your diet, so if you modify your diet to not have as much beef or chicken in it and you prefer to have fish, let's say, for example, you still have to be very careful about which species of fish that you're consuming. And note that the ones that are not recommended to eat include things like swordfish or marlin, mackerel, and shark. Those species are not recommended to eat because they generally have very high proportions of mercury in their body. Mercury poisoning is very serious, as is lead poisoning. It can cause major issues, again, with not only reproductive tissue, but also in your brain tissue as well. Finally, the most obvious marine pollutant is trash, and that's something that we encounter every single day. I'm sure most of us don't even really think about it, right? You go to your local eatery, you order takeout or whatever, you get it delivered to your house, and you just throw it away in the trash can, and from there you take your trash out to the dumpster, but then most of us don't really think about what happens to your trash after that point. Trash that sits in landfills doesn't just stay there. Some of it does get compacted and reduced and recycled, but the vast majority of that trash, whether on purpose or whether on accident, becomes some form of litter, and including trash that sits in these dump sites, for hundreds of years, those materials will eventually end up in the ocean in some way. And so trash is a big problem, not just because it's what we see at the surface, but it's also because this trash, as it breaks down, just continues to circulate in the ocean for thousands of years. The North Pacific Gyre System contains a large garbage patch along each major boundary current. That includes the eastern boundary current, or California current, and the western boundary current, the Kuroshio current. Now note that these patches are not garbage islands, so I don't know where that misinformation came from, but maybe the media sensationalized it at some point. But instead of like an actual physical island of trash, which I know does exist, but it's not, these patches are not like that, okay? So they're not like a massive pile of garbage. They're actually, like, think of them as like soup. So the trash kind of floats around like veggies floating in soup, and it drifts with the current. And so the process that circulates plankton and algae, typically in gyre systems known as Ekman transport, it also will pick up our trash, and it will move it around and around in this cycle across the Pacific Ocean basin. And unfortunately, all of the major gyre systems of the world have these garbage patches within them. And every single year, more of this trash is found in the bodies of various sea life. Seabirds, turtles, and other marine life can not only get caught in this trash and be suffocated, but they can also accidentally consume it, especially the smaller bits of trash and particles known as microplastics. And it's really microplastics that's what we have to worry about, because it's those that do not disappear. Remember that the surface of the ocean, as it evaporates, whatever that's floating in the surface waters gets evaporated right along with it. And if these plastics are small enough on the microscopic scale, they can actually be found in rainwater. And we found actually in Lake Tahoe in California, which was once considered one of the cleanest parts of the world, there's been trash that's found there, microplastics. So yeah, it's not just what we actually see at the surface, not just what we encounter and throwing it out every day, but it's also the microscopic particles of trash that we have to worry about, those plastics. This diagram from the NOAA shows the common types of plastic that are found in the ocean and what happens as it circulates in the North Pacific Gyre. Most of these pieces of trash, they gradually disintegrate into these microplastics. So plastic, the reason why it's such a problem is that, well, first of all, it's very convenient, right? We use plastic every day. You use plastics in your phone, plastics in your computer, plastics in your headphones, plastics, in your food, plastics in everything that you touch. Pretty much everything that we have has some form of plastic. All the food containers that we have, even glass that's, can contain bits of plastic. pretty much everything that we encounter in life nowadays has plastic in it. The problem with plastic is it doesn't break down. It's not biodegradable. And so that includes plastics in the ocean. So unfortunately, any debris that we have, whether it's primarily from boats or nets, or whether it's from things as innocuous as, food wrappers, these materials, they just float and sit around, they drift in the water, and they will gradually disintegrate into much smaller microplastics. Again, that's the main issue that we'll have to face. How do we get all the microplastics out of the ocean, aside from the large debris that we find? Because remember that the circulation of the ocean, the remnant time of the ocean, is about 1,000 years. So that means that as these currents are flowing for thousands of years, the trash is flowing with it. So this diagram shows how long plastics will remain in the ocean. Note that fishing line lasts the longest, and it's up to 600 years. So again, as a comparison, right? 1,000 years for water, 600 years of those 1,000 years, there's like plastic bottle pieces and fishing line floating around. So again, one of the main issues that we'll have to face in the future is, how do we clean the ocean? How do we maintain our oceans for future generations? And we are starting to come up with solutions. There are various species of fungi that are being developed right now by laboratories, I think, in parts of Japan, where these fungi and algae will start to eat plastics, microplastics. So we are coming up with solutions to this that are natural solutions that are helpful to the environment, potentially, maybe. But how we choose to also control our emissions of carbon dioxide and methane gas will have an effect on the temperature variability of the ocean. And without the ocean, keep in mind that without the ocean, we ourselves would not exist. Our species would not be here. Without the ocean and its regulation, we wouldn't have the climates that we do today. So it's vital that in the future, scientists and non-scientists alike, general public, are aware of just how important it is to maintain our ocean for future generations. And I think that with that, we'll go ahead and we'll end this lecture. I hope that you enjoyed it. I hope that you learned something about the ocean today, and thank you for watching this video. I'll catch you in the next one.